Beneath shifting sands and ancient bedrock lies a silent ocean of gas, colorless, weightless, and more abundant than sunlight. This is Earth's own hydrogen symphony, waiting to be heard. Recent studies suggest that trillions of tons of this gold hydrogen slumber deep underground, enough to power our civilization for over 1,000 years. Unlike the electrolyzers and solar arrays we're used to, this fuel has been crafted by geological processes over eons, trapped in rock fractures and hidden reservoirs. Today, we stand at the brink of a new energy era, one where tapping into nature's hidden stash could finally break our fossil fuel dependence and put zero-carbon power literally beneath our feet. Just a few years ago, most experts assumed that free hydrogen on Earth was vanishingly rare. But the U.S. Geological Survey's global mass balance model shattered that assumption by estimating some 6.2 trillion tons of molecular hydrogen scattered throughout the planet's upper crust. This number represents hydrogen produced naturally over millions of years by processes like radiolysis, where underground radioactivity splits water molecules, and serpentinization, which occurs when water reacts with mantle minerals. As these hydrogen atoms migrate upward through porous rock, they can accumulate in traps much like oil and gas, forming vast reservoirs. Only a handful of natural hydrogen seeps have been tapped so far, places like Burakabougou in Mali and Poitou in France. But those early wells hint at the untold magnitude of the resource lying hidden beneath barren landscapes and craggy highlands. Hydrogen is the universe's most abundant element, yet turning it into usable fuel has always demanded high-tech intervention. Green hydrogen requires massive electrolyzer farms powered by renewable electricity. Blue hydrogen starts with natural gas and tacks on costly carbon capture systems to mitigate emissions. In stark contrast, white hydrogen needs no human fabrication. It's simply nature's work, waiting in situ. When we crack open a geological hydrogen pocket, we bypass the need for electricity-hungry splitting or emissions-intensive feedstocks. Since pure hydrogen combusts to yield only water vapor, it offers an unrivaled emissions profile. Imagine heating homes, fueling buses, and generating electricity without belching out a trace of CO2 or sulfur. A promise that becomes tantalizingly real when you factor in the scale of this discovery. From an economic standpoint, gold hydrogen could redefine cost structures across multiple industries. Today's green hydrogen hovers around $4 to $8 per kilogram, largely driven by electrolyzer and renewable power costs. Blue hydrogen, which depends on fossil gas plus carbon capture, can slip just below $3 per kilo with favorable policy credits. But drills repurposed from the oil and gas industry, tapping into existing subterranean reservoirs, could produce hydrogen for well under $2 per kilogram, or even close to $1 in the most prolific fields. That price point undercuts nearly every alternative on the market and would unlock hydrogen's role as a zero-carbon feedstock in hard-to-abate sectors like steelmaking, ammonia fertilizer production, and long-haul transport. Plentiful, cheap hydrogen would not only slash operating expenses, but also catalyze innovation in hydrogen-fueled mobility, from trucks and trains to forklifts and drones. Energy security is another game-changing dimension. Nations that currently import vast quantities of oil and gas could instead drill for gold hydrogen domestically, reducing import bills and buffering against volatile commodity markets. Regions once thought energy poor, landlocked countries without access to offshore oil might discover their own hydrogen riches and leapfrog established producers. In such a future, the geopolitics of energy could be rewritten. Power dynamics would shift away from petrostates toward those with favorable geology, and alliances might form around hydrogen corridors instead of oil pipelines. Moreover, geological hydrogen wells offer a level of dispatchability that intermittent renewables cannot match. When clouds obscure the sun or the wind falters, a hydrogen well can continue feeding turbines and fuel cells, ensuring grid stability. Of course, unlocking this buried bounty is not as simple as drilling and filling tanks. The first hurdle is mapping. We need high-resolution geophysical surveys, seismic imaging, magnetotelluric scans, and exploratory core drilling to pinpoint hydrogen-rich formations. Geological settings most promising for hydrogen accumulation include ancient cratonic shields, ophiolite complexes, and fractured ultramafic rock belts. Once target zones are identified, pilot wells will test flow rates, gas purity, and reservoir pressures. Early data from Mali's Burakabugu well have shown steady flows of 100 to 200 standard cubic meters per hour, but scaling from a single research well to an industrial-scale field requires sustained yields, reliable reservoir engineering, and careful monitoring of pressure decline over time. Drilling technology itself will need tweaks to handle hydrogen's unique properties. Molecular hydrogen is the smallest gas molecule, making it prone to embrittle certain metals and weld seams. Well casings, seals, and surface infrastructure must be engineered or coated to resist hydrogen-induced cracking. Downhole separation is also critical. Natural reservoirs may release mixed streams of nitrogen, methane, carbon dioxide, or hydrogen sulfide alongside H2. Membrane separators or pressure swing adsorption units will be needed on site to deliver pipeline-grade hydrogen that meets purity standards of 99.97% or higher. Building out hydrogen infrastructure, pipelines, compression stations, liquefiers, and storage tanks will demand significant investment, but much of the expertise and materials come straight from the existing natural gas industry. Old pipelines can be repurposed, and lessons from decades of gas handling will fast-track safety protocols, material science, and regulatory frameworks. In regions where pipelines are impractical, hydrogen can be converted to ammonia or liquid organic hydrogen carriers for bulk shipping, then reconverted at point of use. Such flexibility means geological hydrogen could serve local microgrids in remote villages and feed megascale chemical plants alike. Regulatory and environmental oversight will play a pivotal role in ensuring responsible development. Drilling pads, access roads, and water usage all carry ecological footprints. Permitting processes must balance swift deployment with rigorous impact assessments. Emissions regulations should encompass not just CO2 but also fugitive methane, noise, and land use changes. Community engagement will be essential, especially in areas where indigenous lands or biodiversity hotspots overlap with prime hydrogen territory. Transparent benefit sharing, job creation, local energy access, and infrastructure upgrades can turn potential friction into a collaborative win. The timeline for gold hydrogen's rise is fluid but promising. Within the next 5 years, we can expect several demonstration projects that prove up drilling, separation, and supply chains at the megawatt scale. In the following decade, if pilot projects hit performance targets, commercial fields could sprout in multiple continents, feeding hydrogen into power plants, industrial complexes, and mobility fleets. Policy levers, carbon pricing, hydrogen production credits, streamlined drilling permits can accelerate that trajectory. Private capital, hungry for returns in the clean energy sector, may flock to hydrogen startups, while legacy oil and gas majors pivot their rigs and finances toward hydrogen exploration. By mid-century, gold hydrogen could anchor a zero-carbon energy system where renewables, battery storage, and natural hydrogen work in concert. Solar and wind would cover daytime and windy conditions. Geological hydrogen would fill the gaps, ensuring unbroken baseload power. Hard-to-decarbonize industries would swap fossil feedstocks for underground hydrogen, slashing emissions from steel, cement, and petrochemicals. Nations would diversify their energy portfolios, tapping local hydrogen resources alongside imported green hydrogen from sun-soaked deserts. All this hinges on a crucial shift in mindset, seeing hydrogen not merely as a synthetic product but as a geological resource. It's a perspective rooted in humility, recognizing that Earth's subsurface processes have been quietly crafting this fuel since before humans walked upright. By harnessing gold hydrogen, we pay homage to our planet's ancient chemistry while forging a brighter, cleaner future. The hidden ocean of hydrogen beneath our feet offers a once-in-history opportunity. It merges the robustness of traditional resource development with the environmental imperative of decarbonization. The playbook is already partly written by the oil and gas sector, yet the stakes are nobler, averting climate catastrophe and redefining energy abundance. As we sharpen our drills and refine our membranes, we also need to sharpen our policy, our investment strategies, and our public dialogues. Because tapping this silent symphony of hydrogen isn't just about energy, it's about unleashing a new chapter in humanity's relationship with Earth.